Welcome to Descriptive Statistics. Today we are going to explore the foundational building blocks of all data analysis, statistical variables and attributes. Imagine you are a doctor examining a patient. You record numbers like weight and categories like blood type. Understanding the fundamental difference between these two types of data is absolutely critical because it dictates every mathematical tool you will use later in your statistics journey. Let us dive in and build this understanding from the ground up. Now that we have introduced the topic, let us look at what variables and attributes actually are. Why does this distinction matter? Because feeding the wrong data type into an equation will give you meaningless results. A statistical variable is something you can measure, like age, height, or temperature. The numbers have real mathematical meaning. An attribute, on the other hand, is a qualitative label, like gender or hair color. You cannot add or divide hair colors. Instead, when dealing with attributes, we simply count how many items fall into each specific category, which we call frequencies. Building on those definitions, it is fascinating to note that the exact same real-world concept can be treated as either a variable or an attribute. This matters because how you record data changes what you can do with it. Take a person's income. If you record the exact dollar amount, you have a continuous quantitative variable, allowing you to calculate precise averages. But if you ask them to check a box for low, medium, or high income, you have converted that number into a categorical attribute. This makes surveys easier to summarize, but you permanently lose the precise mathematical detail. Before we move on to relationships between variables, let us see this conversion with a concrete example. Imagine a researcher studying car fuel efficiency. They first record the exact miles per gallon for 50 vehicles. Because 30 is exactly 10 more than 20, this exact measurement is a continuous quantitative variable. Next, they group the cars into categories: gas guzzler, average, and eco-friendly. Even though these labels are based on underlying numbers, the text labels themselves cannot be added or subtracted. By grouping the data, the researcher has transformed a quantitative variable into a qualitative attribute, making it easier to present to the public. Now that we understand individual variables and attributes, let us look at how they interact. In statistics, we often want to know if one thing affects another. This brings us to independent and dependent variables. Why is this important? Because it forms the basis of regression analysis and predictive modeling. An independent variable is the characteristic that you, the researcher, change or control. It is the assumed cause. The dependent variable is the outcome you measure, which responds to that change. Think of watering a plant. The water you pour is the independent variable, and the resulting plant height is the dependent variable. This relationship between variables leads us to an extremely important distinction: causal versus correlational independence. Understanding this prevents you from making false conclusions in your research. Causal independence means that physically changing one variable does not cause a change in the other. Changing your shirt color does not change the weather. Correlational independence means the variables do not mathematically move together in your dataset. However, two variables can be highly correlated without any causal link, usually because a hidden third factor affects both. For instance, ice cream sales and sunburns both rise in summer, but eating ice cream does not cause sunburns. So, we have seen how numerical variables relate. But what if we want to see if two qualitative attributes are connected? We cannot use standard equations. Instead, we organize the data into a grid called a contingency table. This matters because it allows us to find patterns in categorical data. A contingency table is simply a matrix that displays the frequency counts for combinations of two attributes. For example, we might have rows for smoking status and columns for lung disease. By looking at the intersecting cells, we can see if the attributes are genuinely connected or if the pattern is just random luck. This brings us to the mathematical tool we use to analyze these tables: the expected frequency formula. Conceptually, this formula calculates what the count in a specific cell should be if there was absolutely no relationship between the row attribute and the column attribute. Let us break down the symbols. E is the expected frequency we are trying to find. R stands for the total sum of the row that the cell is in. C stands for the total sum of the column. Finally, N is the grand total of all observations. If the row total or column total increases, the expected frequency increases. If the grand total increases, the expected frequency scales down proportionally. Let us visualize exactly what this formula represents using a diagram of a 2x2 contingency table. You're looking at a grid that organizes our attributes. The rows represent exercise habits and the columns represent the presence of heart disease. Notice the highlighted cell in the top left? This is the specific intersection where a patient exercises regularly and has heart disease. To find the expected frequency for this cell, we look to the margins. The row totals are on the far right and the column totals are at the very bottom. The grand total, N, sits in the bottom right corner, acting as the anchor for all our probability calculations. Now that we have our formula and visual structure, let us apply it to a concrete example. A local health clinic surveys 100 patients to see if exercise habits and heart disease are independent. We are asked to calculate the expected frequency of patients who exercise regularly and have heart disease, assuming no connection exists. First, we identify our given values. The grand total of patients surveyed is our N, which is 100. The problem states that 40 patients exercise regularly, so our row total R is 40. 30 patients have heart disease, making our column total C equal to 30. We have successfully set up our variables. Continuing with our calculation, we now apply the expected frequency formula. Why do we use this specific formula? Because it assumes the null hypothesis, meaning it calculates the expected overlap if the two attributes are completely independent. We substitute our known values directly into the equation. The row total of 40 and the column total of 30 go into the numerator, while our grand total of 100 goes into the denominator. Next, we perform the multiplication step in the numerator. Multiplying 40 by 30 gives us 1200. This intermediate number represents the unscaled cross product of our two marginal totals. For our final step, we simply divide the numerator by the denominator. Dividing 1200 by 100 gives us exactly 12. This is our final answer. But what does this number physically mean? It means that if exercise and heart disease have absolutely no connection to each other, we would expect exactly 12 patients to fall into this overlapping category, just by random chance. If the clinic observes a number significantly different from 12 in real life, it strongly suggests that exercise and heart disease are not independent, and one might be influencing the other. Now that we have calculated expected frequencies, let us zoom out and understand why this entire topic matters in the real world. Understanding the distinction between variables and attributes is the absolute cornerstone of data science, medical research, and business analytics. If a software engineer accidentally feeds categorical attributes into a machine learning algorithm designed for continuous variables, the system will crash or produce garbage predictions. In medicine, knowing whether to track a patient's exact blood pressure as a variable or their risk category as an attribute determines how a doctor prescribes medication. It is about using the right tool for the right data. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that statistical variables are measurable quantities that answer how much, while attributes are qualitative categories that answer what kind. Second, while you can transform variables into attributes by grouping them, you permanently lose mathematical precision when you do so. Finally, we learned how to organize attributes into contingency tables using the expected frequency formula to uncover hidden relationships. You now have a solid understanding of the fundamental data types in statistics, which will serve as the perfect foundation for your future studies.